Okay, good afternoon. This is our lecture number 36, and in the previous lecture, though I told you that I will first discuss the discretization of Navier-Stokes equations, but as that's a bit lengthy topic, and moreover, whatever we will be discussing in this particular course, our major interest is to discuss the evolution of the interface. So that's why I in certain cases pre-assume that majority of you have already taken the CFD course, so you know the discretization process of Navier-Stokes equations. Moreover, some of you, those who have not taken that course, you have opportunity to take the course on computational fluid dynamics in the next semester, as it will be offered in the next semester also. So there you will be knowing in detail about the discretization of Navier-Stokes equations. And moreover, whatever I will be discussing over here, the evolution of the interface advection, that initially I will introduce it for very simplified version of the problem where you have one dimensional advection of the interface. And second point is, even if we extend this discussion for two-dimensional or three-dimensional situations, then also we will be taking this pre-assumption that velocity field is already known to us from the solution of Navier-Stokes equations. Okay, so we will go with this pre-assumption that velocity field is actually known to us. Once we are making this pre-assumption, then actually we will be able to advect the interface, and I think you will not find much difficulty in understanding the interface advection schemes. Okay. Still, if you feel that some of you want to say have some idea about discretization of Navier-Stokes equation, so already I have some recorded lectures for this topic. So in this particular slide, I have mentioned the detailed required set of 5 lectures, which like one need to go through if you have to understand in detail about the discretization of Navier-Stokes equations. Okay, so link you can find over here. I will be posting this lecture on Moodle, and then you can go through these lectures if you want to know about this. Okay, now we will go to our main topic, which is nothing but interface. And if you recall, then in the last lecture about the interface, we have seen that there can be different mathematical functions which can define the shape of the interface, okay, at a particular time instant. Then at that time instant only we can define tangent vector, we can define normal vector to the interface, and third important point was curvature of the interface at any particular point. Okay, so these three informations were very useful in adding the surface tension force and estimating the surface tension force into our governing equations, which is nothing but momentum equation. Okay, now along with this, what will be happening, that interface will not be remaining stationary. Okay, so when you are having the flow of the multiple fluids, then interface will be evolving with space and time. So at a particular instant, you can define some mathematical function which is actually describing the current shape of the interface or current location of the interface. But what will be happening when interface is evolving with space and time? So ultimately that function has to evolve. Okay. So how that function will be evolving, and on a computational grid, what are the different discretization techniques which we can use on interface evolution equation or interface evolution function, so that we can correctly predict the value, the location of the interface in each of our computational grid cell during its evolution with time. Okay, so we have already seen that for defining the interface we can have some height function. Okay, we can have some height function hi of x, which will be equal to 1 if x position is on fluid I, and it will be equal to 0 if x position is not on fluid I. So it means this height based step function will be 1 for fluid 1, and it will be 0 for fluid 2, and we will be having some sharp discontinuity at the interface. Okay, now if I have to see the propagation of the interface with space and time, So what I need to do, I need to know that how my height function is actually evolving with space and time. So ultimately, if I assume that I don't have any type of reaction involved and any type of phase change heat transfer involved, in that case, I will be finding that across the interface there is no flow from fluid 1 and no flow from fluid 2. So ultimately interface is just moving from one location to other location, but it is not having any, interface is not receiving any fluid, okay, or no fluid is actually going out of the interface. So it means material of the interface, entity of the interface should remain conserved. Okay, so that's why what I can do, I can write that total derivative of the interface dH by dt has to be equal to 0. Okay, now total derivative can be further written in terms of del H by del T, that is local derivative plus u dot gradient of H, which is nothing but advection of interface with the space. Okay, so now here one important point, physically you can relate that the rate at which value of this H will be changing with time, that will be dependent upon the rate at which it is actually advecting with the space, because ultimately this term will be going on the right hand side. Okay, so evolution of this height function with time will be simply equal to nothing but the rate at which it is advecting because of the flow velocity. Okay, is this one clear? Now of course, for certain methods, this type of sharp continuity based height function will serve the purpose, but there are certain methods for which actually rather than using this type of method, this type of function, some other type of function can be employed, and that is called as a color function. Okay, so color function is, say I have a two-dimensional computational cell. So if I have a two-dimensional computational cell, then for two-dimensional computational cell my width will be unit, and these are the two dimensions, say delta x and delta y. Okay, so if you see the definition of this color function Cij, so say the location of this cell is nothing but my I comma j. Okay, so this is my I comma jth cell. So for this I comma jth cell, if I have to define the color function, it is becoming equal to 1 by delta x into delta y, which at the moment I can simply say for a two-dimensional cell is nothing but volume of the cell. Is this point clear? For a two-dimensional cell, considering unit depth, it can be considered equal to volume, and if I have a three-dimensional cell, then I can simply call it as a volume of the cell. Okay. Now I am doing volumetric integral of height function h of x comma y, and then here I need to use dv, so dv will be dx, dy and y. Okay. Now you can clearly see that the cell which is occupied with fluid 1, for that this height function will be unity everywhere throughout the cell, and ultimately I will get nothing but value of Cij equal to, no, height function will be 1 for fluid 1, so value of Cij will be equal to 1. Okay, so Cij will be becoming equal to 1 for fluid 1, and Cij will be becoming 0 for fluid 2, and the cell which is containing part value of fluid 1 and part of fluid 2, for that particular cell the value of Cij will be in between 0 to 1. Is this point clear? Okay, and I can simply call this color function Cij as nothing but my volume fraction of fluid 1. Is this point clear? So from this mathematical definition you can say that Cij is nothing but representing the volume of fluid 1 present in a particular cell divided by total volume of the cell. So that's why it can be called simply as, this color function can be simply called as nothing but volume fraction of fluid 1. Okay. So this is the second type of function which we should know, because all this we will be like using when we will be seeing different advection schemes. Okay. Then third is another function I am having. I am calling this function as indicator function. Okay. And indicator function is nothing but it is used for smoothing of the interface. Why smoothing of interface is needed? Interface on a macroscopic scale is a sharp discontinuity. Okay. And my height function as well as this color function, they are able to prescribe a particular sharp discontinuity. Okay. But ultimately, whenever you will be using the one fluid formulation, in your one fluid formulation, you have to transfer the properties at the interface from fluid 1 domain to fluid 2 domain. Okay. So the cells for which the value of color function is completely 1, there you can simply take the properties of fluid 1. Cells which are fully occupied by color function equal to 0, there you can simply take the properties of fluid 2. Okay. But the cell which is at the interface, there is a jump. Okay. So if now you transfer the property from fluid 1 to fluid 2 using some jump condition, that may lead to some numerical artifacts in the computational procedure. Okay. So what we need to do, we need to do some smooth transition of properties from fluid 1 to fluid 2 near the interface. So for ensuring that smooth transition, what we need to do, we need to smoothen our either this height function or this color function, because height function, color function, all these are nothing but discontinuous functions. These are not creating a proper continuity or smooth transition at the interface. These are creating the sharp discontinuities. Okay. So as these are creating the sharp discontinuities, in order to transfer the properties from fluid 1 to fluid 2, we need to do smoothing of the interface. That's why either if I take H or if I take C, I need to multiply these with some function G, which is called as smoothing function or smoothing kernel. Okay, so this is the smoothing function. Mathematically, how this function will be used, so for different schemes there are different approaches for using smoothing in order to determine the indicator function, but at the moment just a generic form I am using, where g of x minus x dash and y minus y dash can be of any form. Okay, and this is nothing but a smoothing function. Up to this point, is it clear? Now you can see in the bottom there is a computational grid. Okay, so this is like a one-dimensional computational grid, because in one-dimensional computational grid what will be happening? You will be having only locations in one dimension, and in second dimension and third dimension variation of the properties will not be there. So what is the meaning of one-dimensional computational grid? One-dimensional computational grid, you can just assume the replication of some problem where, say, you have a pipe, and in this pipe you have some ideal liquid which is entering to this pipe. Ideal liquid, the meaning is a liquid of zero viscosity. Okay. So when an ideal liquid of zero viscosity will be entering the pipe, and say on other side of the pipe you have air. So you will be finding the formation of a straight interface. Why straight interface? Because you have ideal fluid. There is no viscosity. So it means your velocity profile at each and every cross section in the liquid will be just uniform. So as you have uniform velocity at walls as well as at the center and all the locations in the vertical direction, so your interface will be propagating linearly with time in that particular pipeline. Okay. So for this situation, if you have to computationally solve, what you need to do, you need not to see the variation of properties in y direction, you need not to see the variation of properties in z direction. So ultimately you can represent your grid structure simply like this, that say this is your jth cell, this is j minus 1th cell, and this is a j plus 1th cell. Likewise you can represent. So your elements will be nothing but simply the line elements. Okay, or even if you assume some area, of course that area will be identical to the dimensions of that particular duct or pipe, whatever I am considering. So in this area only the fluxes will be estimated, but in vertical direction there will not be any variation. So if variation is only in single direction, then all these grids I can nothing but represent with the help of single set of indices. Is this point clear? So whenever I have a computational grid, and in that grid the variation of properties are happening in both directions x and y, then I need to use two different set of indices, I and j. Say I represent variation in one direction, j represent variation in other orthogonal direction. Okay, but if I have one dimensional problem, then I will be having the variation only in the one direction. So that single index I am using j over there. Okay, now this is the representation of a say grid. So here you can see this is your jth cell, this is j minus 1th cell, and this is j plus 1th cell. Now you have seen the mathematical definition of all the functions. So if you see the mathematical definition of function h, it represents that the location up to which interface is there, its value will be 1. Okay, where we have fluid 1. So let's assume that up to this point I have fluid 1. So up to this point its value is 1. Then at the interface it is immediately going to 0, and after that it is having value 0. Okay, so on a computational grid, this is the representation of this function h of x. If you have to represent the color function, which is nothing but identical to that of a volume fraction of fluid 1, then you can see that this particular color function, this cell is completely filled with the fluid 1. So that's why this shaded gray color is representing the volume fraction equal to 1. So entire cell filled with fluid 1. Then second cell is also completely filled with fluid 2. So this is also, fluid 1. So that's why this is also shaded, fully shaded gray color. Then if you see this particular cell, in this particular cell, from our height function we already know that fluid 1 is only in this portion and the remaining portion is nothing but a fluid 2. So it means the value of C for this particular cell will be nothing but in between 0 to 1, depending upon the volume it is occupying over here. Is this point clear? So now you can see that when I have shown the value of color function, then you can see the value of Cj is only this much portion is shaded. Okay, is this point clear? And after this point, I nowhere have the presence of fluid 1. Everywhere there is fluid 2. So value of color function will be 0. That's why there is no shaded gray portion. Okay, is this point clear? So this is my representation of the second type of function. Then I told you that third type of function I will be using an indicator function, which is multiplying some smoothing kernel, and depending upon the value of this, the type of this smoothing kernel, it will be leading to smooth transition of interface from one computational cell to the other. So interface as per the smoothing function, the transition from 0 to 1 will not be in a single computational cell. So for height function and color function, interface transition from interface is happening only in a single computational cell. Okay, but for indicator function you can see this complete zone is actually leading to smooth transition from fluid 1 to fluid 2. Okay, and what is the role of course your interface is not thick, but what is the role of indicator function? The role of indicator function is just to ensure the smooth transition from fluid 1 to fluid 2, so that this indicator function can be later used to smoothly correlate the transition of properties from fluid 1 to fluid 2. Because if you have sharp jump in defining fluid properties only at the gap of a single cell, your fluid properties are changing by the time, say, by the gap values of 1000. For example, if you use air water system, so then gap from fluid 1 to fluid 2 will be 1000 in this one. Yes, about 100 orders difference in viscosity. So that much sudden jump in the properties will lead to numerical errors. So we have to ensure the smooth transition of properties. So for that purpose, we will be using function Ix. Now you may recall one more function f of x I have defined earlier, and that function f of x was nothing but the one which represented smooth transition. It was a smooth function, and the name of the function I had given level set function. Okay, so if you recall the previous lecture, in the last lecture, when I was explaining about the different functions which can relate or which can mark the presence of the interface, there I defined one level set function for which value of function is equal to 0 marks the location of the interface, and in one type of fluid value is greater than 0, in other type of fluid value is less than 0, and that value is smoothly transitioned over the entire volume of the fluid. Okay, so you can see over here this f of x, if I say my level set function, then at the point of interface its value is 0, and whenever you are moving towards the fluid 1 its value is becoming greater than 0. However, as your distance from the interface is increasing, the magnitude of this value is also increasing. Okay, and in fluid 2 this value is less than 0, and as you move towards the fluid 2 this magnitude is again increasing. Okay, so once the knowledge of these functions is clear to us, when we have represented it on a computational grid structure in one dimensional system, now we need to further dig into this, and what we need to do? We need to see that how all these functions now will be advecting with the time. Okay, if flow is happening, so till now problem I have explained. So we have shown the computational structure and different functions which are marking the present location of this physical phenomenon. Okay, but in this physical phenomenon what will be happening? In this particular physical phenomenon, depending upon the velocity of the liquid, what will be happening? This interface will be moving towards the right side. Okay, so how this interface is moving towards the right side, it means the solution of this particular equation now we need to determine. Is this point clear? So let's see the solution of this equation. So now solution of equation means we are talking about advection, and in this present case I am showing you advection of the color function. Okay, color function means the function C. Okay, so once you are talking about advection of the color function, your equation will become del C by del T plus velocity times del C by del X is equal to 0. Is this point clear? And let me consider that at the moment I have one dimensional flow. That's why I need to specify velocity only in one direction, and the value of that velocity is u naught, which is constant. It means it is not changing along the flow. Okay, and this value is nothing but already known to us. Okay, so what I am assuming at the moment, that I already know the value of the velocity at the interface, and value of this velocity is actually remaining constant as we are moving along the pipeline, what I have actually explained in the physical situation. Okay, so with this assumption, let me a little bit extrapolate this. So equation was this, plus u naught times del C by del X equal to 0. Now I have taken u naught is a constant, I have taken it inside this derivative, and then c into u naught I have written as f. Okay, where f is nothing but, what is term del f by del x? Convective term, and we always know that the physical nature of the convective term, or from our control volume approach we have seen that this term comes nothing but from the net flux across the boundaries of the control volume. Okay, so I can say this f has nothing but my flux across control volume. Okay, and whose flux I will be calling? This is nothing but flux of color function. Okay, because u naught is velocity and this u naught is getting multiplied with c, which is color function. So my term f is nothing but flux of the color function across the control volume. So all are clear with this point. Now if I need to solve this advection equation, what I need to do? I need to integrate this equation over the time. Okay, and this del f by del x I need to integrate over the space, which is nothing but equal to that of flux across the control volume. All are clear with this point? So now I can assume that value of color function at jth cell is known to me for time t. Okay, and I need to calculate the value of c for jth cell at time t plus delta t. This is how I will be advecting the solution. Okay, so let me call the value which is at time step t, I am indicating time step with superscript n. Okay, then if n is my number of time steps, then at time t plus delta t, if delta t is time step, then my value at t plus delta t can be indicated as value at the next time step, that is n plus 1. Okay, so now if I apply this time integration, I can write that Cj at n plus 1 will be equal to Cj at n minus 1 by delta x into this entire quantity is nothing but representation of the flux. How do you calculate flux? So say if you have to calculate in CFD del f by del x at jth cell, how you will be calculating? Using say central difference scheme. How you will be using? Value of flux at the right boundary. So right boundary is, if say j is my cell, if j is location of the cell, then what will be its right boundary? J plus 1 is next cell. So boundary between these two control volumes will be at half distance. So that is j plus 1 by 2. Okay, and left boundary will be at j minus 1 by 2. So if I have to calculate del f by del x at jth cell, then flux will be always defined at the boundary. Flux will not be defined at the center of the cell, because flux is something, advection flux is something which occurs at the boundaries. Okay, so one boundary is at j plus 1 by 2 minus second boundary is at j minus 1 by 2 and divided by delta x. So this is my one part, and this particular term I can write as Cj at n plus 1 minus Cj at n divided by delta t. Okay, using the forward difference scheme. So then I can write this Cj at n plus 1 is equal to Cj at n, and because in terms of time I am representing it in the generic form, so that's why I am writing it in terms of integration at the moment, that integration from t to t plus delta t of these fluxes with time. Okay, so up to this point all are clear. Now if I need to determine the value of Cj at time n plus 1, then I need to know what is the functional form of the fluxes with time. Because if I know the functional form of the fluxes with time, then only I can do this integration. Okay. or moreover, I have to do numerical computations. So numerical computations means I need to approximate this actually. Okay. So the very first approximation which we can assume is, once again, one important point let me specify to you. Whenever we will be doing the advection of the volume fraction, always we maintain one condition numerically, that the jump of the volume fraction function or height function or color function, whatever function you consider, the jump of this function or jump of the interface should not cross multiple cells simultaneously. Okay. So when your function or interface is moving, then it should move from one cell to its next adjacent cell. It cannot cross multiple cells at a single go. Why it cannot cross multiple cells at a single go, that you will be understanding in the next slide. Okay. So before that, one condition we are imposing, that whatever the delta t I have to select, this delta t I have to select in such a way so that my delta t into u naught, this is nothing but the linear distance which interface can move, that has to be less than equal to delta x. At max it can be equal to delta x, otherwise it has to be less than delta x. Is this point clear? So one condition we are invoking, that when interface is advecting from one cell to next cell, it should not take jump of multiple cells in a single go, it should only take a jump of single cell. This point is clear? All are clear with this idea? So that's why the one time controlling condition you may find in case of Navier-Stokes equations from the CFL criteria, which will be limiting your time step if you are using explicit time integration scheme. Similarly, one time step limiting condition you are finding from your interface advection equation. Okay, and now when you are simultaneously solving the Navier-Stokes equation and the this interface advection equation, then you have to check first both the conditions, and among both, whatever is lowest time step, that you have to choose, because you have to satisfy both the conditions. Okay, is this one clear? So this condition is, say, we have satisfied. Now if you recall, or say some of you, those who have taken the course on CFD, they may recall that when we talk about the advection terms in our Navier-Stokes equations or in any equation, say scalar transport equation, etc., then the use of central difference scheme is actually not considered, because central difference schemes for advection terms does not satisfy one important characteristic of the numerical schemes. The name of that characteristic is, many of you have taken course on CFD. So there are three characteristics. One is, yes, boundedness. Boundedness is not the answer of this, but names are boundedness, transportiveness, and conservativeness. Okay, so whenever you choose a numerical scheme, your numerical scheme for fluid flow problem should have three properties. It should be conservative, it should be bounded, it should be transportive. So if you use your central difference scheme for discretization of the advection equations, then you will be finding that that particular scheme is not transportive. Okay, so that's why for advection terms we particularly go for upwind type of schemes. Okay, so this is something which we study in basic CFD. So let me over here consider that I am considering that I have piecewise constant approximation. What is the meaning of piecewise constant approximation? if you know from your CFD, then you will be understanding that in case of piecewise upwind constant approximation, what we do, the value of flux we specify nothing but equal to the value of property of that variable in the cell of upstream direction. Okay, so if you have flow from left to right and you are considering your jth cell, then any direction above that is actually your upstream direction and any direction down of that is your downstream direction. Okay, so typically when you estimate the flux, then we simply consider that if I need to estimate flux at point j minus 1 by 2, if I consider my piecewise upwind constant approximation, then I will be writing the value of flux nothing but equal to the value of the field variable, which is their cell averaged value of the field variable, which is there at the just previous node in the upstream direction. Okay, so likewise if you calculate f of j plus 1 by 2, so f of j plus 1 by 2 is, you are calculating f at this particular point. Okay, so if you calculate at this particular point, then just previous cell is having value Cj, so you can write that your f of j plus 1 by 2 is nothing but Cj into u naught. Okay, u naught is constant. So as u naught is constant, so u naught is taken outside, and now this integration will be converted into algebraic equation because I have estimated the flux as a constant parameter. So integration of this entire is nothing but equal to delta t. Okay, so u naught delta t by Cj, and when I will be calculating flux at point j minus 1 by 2, then I will be considering the value of color function in the cell j minus 1. So that is what I have written, minus Cj minus 1. All are clear with this point? Now, at the moment what you will be knowing, say this is your initial interface location. In this direction, if you have say 10 grids, 1, say this is first grid, second, third, fourth, likewise you may have multiple grids. So at all the grids, you know the value of C at time t. Okay, because you know what is initial location of interface. That is something which you are specifying. Okay, so by knowing initial value of interface, you know that at all these cells your value is nothing but 1, and for all other cells values is 0. Now you have got this equation. This equation, if you know the values at time, so here also you are calculating all these values at nth time step. Okay, so now if you know all these values at nth time step, you know delta x, you know delta t, you know u naught, you can calculate the value of Cj at time n plus 1. Is this one clear? This is a simple equation, explicit equation. You have to just write one simple for loop and you can calculate for all your grid points. Okay, now you see the solution. So solution is for a physical problem where I assumed that I have same type of channel, and in this type of channel, this is my fluid 1 and rest everywhere I have my fluid 2, and this fluid 1 is moving towards the right side with velocity u naught. This is the problem which I have taken. Okay, now in this problem, say this is the value of the color function C at black colored line. This is say at some time t. We know that when theoretically this solution will be propagating, say this is at some time t equal to 0. So when this type of slug of the fluid 1 will be moving in the forward direction, what will be happening? What will be happening? It will be simply translating, okay, one dimensional flow. So it will be simply translating in the forward direction without any change in its shape because it is moving with constant velocity. So there is no compression or stretching of the interface. And also the nature of the phenomenon is one dimensional, so that's why there will not be any curvature across the interface. So if theoretically, say I calculate that the new location of this at some time t equal to 140 times of time step, after 140 time steps, then theoretically my black colored line will be the situation. So that is the theoretical condition. Okay. And if I have to calculate the same value of this interface after 280 times, then this should be my situation, that it has reached. So whenever time is passing, it is reaching towards the right side of that pipe. Okay. But there is no change in its shape. So that's why its color function should remain ideally, or theoretically its color function should remain intact. Okay. But if you apply this previous equation, if you apply this particular equation, so you can consider that, say your length scale from one end to other end is, say, unit 1, and in this length scale, if you have taken your 200 grid points, how many points? 200 grid. So 200 grid points are actually too much number. Why too much? You cannot say too much is, why I am saying it's too much, because say this slug is actually being covered in only 20 cells. Okay. So within the slug itself also you have about 20 cells, and then overall in the entire domain the total cell count is 200. Now over these 200 grids, if you apply this particular equation using a space and time loop, you need to apply two for loops, then you can see that, of course, at the initial times theoretical and numerical solution will be same, because you are introducing the initial condition in the solution. Initially you have to tell that, okay, for all the grids what is the value of C. So once you specified value of C for all the grids, it will be following exactly the ideal distribution. But when it is propagating with time, and if you plot the numerical solution of C after 140 time steps, you will be finding solution something like this. So interface has lost its nature. Okay, so it has become something else. So it is widening in the direction of the flow. Then if you see further after 280 time steps, then you can see it is even further. Okay, it has further widened. So it means that it has become a problem now. Because ultimately what is our interest? Whatever equation we have in hand for determining the spatial and temporal evolution of the interface, when we are solving that interface numerically, that is not giving me the proper value of the interface. Rather we are getting some diffused type of interface. Okay. So now, and all of you, I suggest that for doing this you need not to do any CFD course or anything. This is a simple equation. If you know little bit of programming, please do this problem by your own and try to get this blue colored line. Okay, so you can simply do this. I have explained you the physical problem also, and I explained you the process how you have to do it. Okay, so what you can do, you can write a small code and then you can try reproducing this result, whether you are getting this type of behavior of the color function or not. Okay. Okay, now let's go further. Now let's consider that one wrong assumption we have made over here. What was the wrong assumption? We assumed that, what was the wrong assumption? Why this solution is wrong? Can anyone guess what is the wrong assumption we have while we have taken this approximation? Any one of you can guess it? Let me go to the equation part now, you see, and then tell me. You can see the photo also.
Differential parts है इसमें जो error का term हम छोड़ देगा.
No, not that. That will be only a fixed truncation error of smaller magnitude, not that much high. See, whenever we do errors, there are two types of errors in CFD. One is truncation error and other is round off error. Okay. So, if it is caused because of the truncation error, you know that you are not changing the grid size. Grid size is same throughout the entire time. So, order of truncation, if this error is because of the truncation error, then order of the truncation error should remain same with time because you are not changing delta x. So, then if this is this much smeared up, then this also should have been of the same type. Okay. So, that is not the reason. Now let me tell you what we have done over here. We have made this assumption that the flux of C which is entering this cell is nothing but the complete value of this is going to the next cell through this boundary. In the same way, here I assumed that this value of Cj has transferred to the next cell. Okay, this value of Cj has transferred to the next cell. Now you consider your cell as nothing but a container. If your cell is a container, because it's a volume, so it's a container. So if cell is a container, then this container first it should get filled. When this fluid is coming from left, first this container should get filled and reach the top mark. Once it has reached the top mark, then only it should transfer the value of C to the next cell. But at the moment, what your scheme is doing, at the moment, even if it is partially filled, this scheme is transferring that partial value to the next cell. So what will be happening in this way? If you are not filling a single container full and just before filling transferring whatever amount it is having to the next cell, then that amount will be distributed among the multiple containers and in a single container its peak will decrease. Is this one clear? So that is what is actually happening over here. Of course you are taking a pipe, but when you are doing computational simulation, then what you are doing? This pipe you have divided into 200 small control volumes. Now one of the control volume is actually filled with the interface and rest control volumes are at 0. So you are transferring from this pipe to this volume to this volume to this. Now are you understanding? So that is what theoretically it is same. So that is what I am saying that. So whenever you do theory and whenever you do computation, so whenever you do experiment or physical situation or whenever you do computation don't know what is physically happening. Okay, so physically you can interpret and your experiment can show. But computation will be working only based on the equations what you are solving. Okay, and how you are solving. So that's why our interest over here is to advect the interface using computational procedures. Okay, so that's why our intention is to determine the correct numerical scheme. So we have to look this problem from the computational perspective only. Okay, so is this point clear what I explained to you? Because what we are doing, whenever we are dividing this into smaller volumes, smaller containers, we are not filling one container when the fluid is coming into this, and before filling we are actually passing the partially filled volume to the next one. So this way large number of cells we will be finding which are filled with partial volume, and in every cell we will be finding that with the passage of time, if say all volumes are just partially shifting the values to their other neighboring containers, then we will be finding after some time almost all the cells will be filled with the partial volumes. Okay, after long evolution of time. So that is what is happening actually in this particular case. Okay. Now what is the solution? So one solution we can now propose is, instead of going for the piecewise constant approximation, we can use piecewise linear approximation. Okay. The meaning of linear approximation is, that in each cell I will be defining some slope. So this is the slope here, this is the slope here. So based on this slope, what will be happening, rather than transferring the total cell volume, the part of the cell volume will be actually transferring to this point. So here you can see that this was the initial volume, say this was the slope in this cell. Now when you will be propagating the solution, then this slope after some time delta t will be going to this point. So now what has happened? Only partial volume from the first cell has entered to second cell, not the entire volume. Point is clear? So only partial volume has come from this to, so this is the portion of the added volume from this cell to this cell. This point is clear? Now in the similar way, if this was the slope for the, say this was the slope for the next cell, now this slope will be transferring to this. So now then only this much portion has gone to next cell. So what we are doing, somehow we are trying to adapt a situation that we will define the slope in such a way which will be giving some indicator that to some extent if my this cell is not filled, then first let it fill and then transfer the property to the next cell. Okay, but we are not able to fully do this because slope will also cannot take the 100% volume. It will be ensuring the transport to some extent. Okay, so how this is done, now here approximation will become little bit complicated. How? If you take your this slope, say this is the slope Sj minus 1, then by doing some small geometric computations you can calculate how much volume has entered into this cell during time interval delta t, and the flux across this cell will be becoming equal to flux at j minus 1 by 2 will become equal to Cj minus 1 n plus delta x minus u naught dt into Sj minus 1 by 2 into u naught delta t. Okay. So now the entire constant value is not transferring, but the value transfer is dependent on the slope. Okay. And in this slope, if you just using this slope, if you do little bit of geometric manipulations, you will be finding that flux across this boundary will come out to be this value. The meaning of flux is, this was the line, original volume. Now this line has in time interval u naught into dt, it has shifted through this distance u naught delta t. Okay, so now how much volume it has displaced, so this displaced volume will give the flux across this interface. Is this point clear? Process I have told you, you can now try, do geometric computations and then calculate this. Okay, all are clear with this point? In the similar way, if you first assume this to be your cell, then after delta t this is the cell, then this volume which has changed, that is the volume which has actually moved across the right boundary. Okay, so using this you can calculate now the fluxes, and if you substitute these fluxes, instead of substituting the value of f what I have specified earlier, a constant value, now if you specify the value of f like this, then you will be finding this particular equation where lambda is nothing but equal to your u naught into delta t by delta x. But here you have to take care of one more important point, that along with knowing the value of c, you also have to know the values of these individual slopes. Okay, so how the values of individual slopes are calculated? First the value of slope, first the value of say slope is calculated for this j plus location. Okay, j plus means we are talking about the right face. So if I need to calculate the value for right face of the slope, then if I assume the linear interpolation, then I can consider value to be average of this cell and the next cell. So that is what I have done. So Sj plus is nothing but Cj1 at n minus Cj at n divided by delta x. Point is clear? Then similarly, if I need to calculate Sj minus, so here j plus and j minus are representing the, plus is representing rightward face, minus is representing leftward face of the control volume. Okay. So if I need to calculate Sj minus, then Sj minus is having the neighboring particle, so Sj minus face is shared by cells j minus 1 and j. So the difference of their color function Cj at n minus Cj minus 1 by n by delta x, that will be giving me the value of slope. Okay. And if I know the slope of this line at this particular boundary and value of slope of this line at this particular boundary, then mean slope of this particular computational cell I can calculate by using this coefficient, by using the weighted average of these two values. Okay, so here you can see the weighted average. For defining the weighted average, I have used some arbitrary constant k. Once k is equal to 0, the meaning is slope is equally shared by the values of slopes known at the faces. Okay, is this point clear? But once I use different values of k, then I will be giving the preference to some particular direction. Okay. Now you can see the solution using this equation also. So this is the solution. This was the theoretical solution I have already explained. Now computational solution, you can see this red colored line is corresponding to k equal to 0. This blue colored line is corresponding to k equal to 1, and this is corresponding to k equal to minus 1. So here you can see that though to some extent you are able to preserve the value of c, okay, but it is having some oscillations, and whenever you are growing with time, so these oscillations are still actually prevalent. Okay, now if you have this type of oscillatory solution for the color function, your interface means it will be becoming something unphysical. So again, this type of like the upwind differencing scheme, which we were successfully using for solving the flux of velocity field. When we solve Navier-Stokes equations, then we calculate momentum flux across the boundaries, and for solving momentum flux across the boundaries, our upwind differencing scheme is working perfectly fine. Whenever you go through the solution of computational solution of Navier-Stokes equations, then you will be seeing that that scheme is perfectly working fine. But whenever we are applying the similar approaches for advection of the color function, actually we are finding so many irregularities. The issue is, in case of single phase flows, entire cell is filled by same type of fluid and it shares the same value of the velocity. So that's why there is no error. But in this case, the color function is something which represents the fluid 1 and fluid 2. So, and fluid 1 should transfer to fluid 2 only if one cell is completely filled by fluid 1. So that is our nature. Okay. So that's why, because of this, we are finding actually so many errors in this solution. So it means this approach is also not workable. So once this is also not workable, then we have to go for some more advanced schemes. Okay. So let me stop here only today, and then I will discuss the other interface advection schemes in the Monday's lecture.